All right, so welcome to the 16th video in Introduction to Quantum Field Theory. This one will talk a little bit about the interpretation of the Klein-Gordon equation, or specifically the Klein-Gordon Lagrangian. So before we get into that, I would like to discuss an error that I made in a previous video, and I didn't catch it until now. This is a little embarrassing, but I think this was video 6 where I talked about wave mechanics. I was talking about phase velocity, and I said that massless stuff, you have a phase velocity of the speed of light, and for massive particles, you have phase velocity less than c. This is actually not true. So what I, for some reason, forgot to mention was that there's actually a concept called group velocity. Phase velocity tells you the speed at which a plane wave moves, and group velocity tells you the speed at which a wave packet moves. So just to kind of go over what the difference is. A plane wave is like this, but say you have lots of different plane waves that constructively interfere in just the right way. So you have like a bunch of these, and you just add them together, and maybe you have a bunch more. Well, then what it ends up being equal to is some kind of wave that goes like this, and this is called a wave packet. And so you end up with the phase velocity is the speed at which this blue line will oscillate up or the speed at which this blue line, but then you end up with something called group velocity. So let me call it this. Let me say that this right here is phase velocity, so a little phase. And then the point at which this center point of this kind of packet, the center point, the speed at which that moves, this is the group velocity. And so the phase velocity will actually move more quickly for a massive particle, but the group velocity will move more slowly. And this is because the phase velocity is defined as the ratio between the frequency and the wave number, but the group velocity is defined as the derivative, the partial derivative of the frequency with respect to the wave number, which makes sense. The phase velocity tells you how fast the plane wave's moving, and the group velocity essentially tells you how how that varies, what the variation is, and that variation is going to, of course, is going to be related to this group velocity, which makes sense because this group is kind of like if you can only look at it by saying that there's a variation in the size of the plane wave. So it's by basically considering all the different plane waves that add up to make this wave packet. So in the massless case, the phase velocity is c, and the group velocity is also c. But in the massive case, you do not have this simple linear relationship anymore. You have that the phase velocity is actually greater than the speed of light because of this right here. And you have that the group velocity is actually less than the speed of light. So for massless particles, the phase velocity and group velocity is the same. For massive particles, they are different, and the group velocity is less than c. And this would be what we would traditionally think as the speed of a particle. Not so the individual waves are not particles, but the sum total of them makes a wave packet, which is particle-like. So this is what I wanted to correct. So let's move on to talking about the Lagrangian. The last video introduced the Lagrangian density in order to derive it. the Klein-Gordon equation, but it didn't talk about its meaning. So let's write down the Lagrangian again. It is double partial, or nope, it's this minus m squared phi squared. And we can break this into parts. So the d naught, partial naught phi, then plus the space-like terms minus m squared phi squared. And the space-like, or the space, this, it's not space-like, the time-like components, the contravariant and covariant, they are the same. So you can just bring that down. But then the contravariant derivative is actually the negative. So you get a negative sign here. Phi j phi minus m squared phi squared. So this is how this looks. You get the time-like component, space-like component, and then the mass term. So what do these correspond to conceptually? Because if you recall from video 7, talked about how the Klein-Gordon equation kind of models a spring mattress, an infinitely a compact spring mattress where all the springs are connected to each other. And we call those springs in the field, we call them field oscillators. So this term right here, this is actually the kinetic energy of those field oscillators. And this one, this term right here, the space-like term, is actually the potential energy between field operators. Not operators, oscillators. Easy to get those words confused because they sound similar, but they have very, very different meanings. And then this right here, the mass term, is the potential energy of the field oscillators. So if you imagine that a or what do you call it? That a scalar field is like a spring mattress, and at every point in space there is a spring connected to its neighboring point spring. Then the this term will give you the kinetic energy. It'll tell you how that spring is moving, and then this one will tell you how when it moves, how it creates potential energy between it and its neighbors. And this one tells how much potential energy is stored in that spring itself. And so this is how you can conceptualize, think about the Lagrangian. So therefore, the Lagrangian, which is the integral over space of the Lagrangian density, is the kinetic energy of the springs minus the potential energy relative of the what do you call it, the between the oscillators, and then minus the potential energy of the springs themselves. In the case that this term is equal to 0, so the springs don't store any individual energy, this means that the mass is equal to 0, and then that the behavior would be like this. So if the springs don't store energy themselves, then they travel at the speed of light, their maximum speed. But if the springs store energy, which basically means that they are massive, then they travel less than the speed of light. And so that this is the the conceptual stuff that it's good to understand from, or like from the Lagrangian, is that mass basically corresponds to having a spring at every point that can contain energy on its own separate from relationships between oscillators. But massless means that there is no potential energy of those field oscillators. So the only potential energy is stored between springs at different points. And if you do that, then it turns out things must move at the speed of light.